Alright, so here we go again in this second video that we have. So in this video we will going to discuss the wave nature of light. So technically we will focus on one thing, what is called here polarization. Alright, so in the previous lesson we talked about the different parts of your electromagnetic wave. So we have the wavelength, then we have the frequency, and we have the velocity. So in an electromagnetic wave, the velocity is constant, so that is 3.0 times 10 to the 8 meters per second. Alright, so in this lesson that we will talk about today, so we will discuss one of the two natures of light. So there are two natures of light, which is the wave and the particle nature of light. So in this lesson, we will talk about what are some ways that the light behaves like a wave. So if you remember your lesson about waves last time, so what are the things that we can consider that makes a light a wave, right? So these are the objectives that we were going to do. So explain the interaction of polarizer using the wave theory of light. So how polarizers are used, or how can what are these polarizers? All right, next. Yeah, so that is the objective for this particular lesson that we will have. All right, so let's get started. Alright, so one property that tells that the light is a wave is called diffraction. Alright, so diffraction happens on sound and also on water waves. Alright, so when diffraction happens, interference occur. Alright, so okay. Now, just like your water waves and sound waves, your light also do interference, diffraction, and polarization. So, common characteristics of common things that we can find on a wave. Right? So, these three. So, we have it right here. So, I will activate my pen. Alright, so we have it right here, which is called the interference. So a wave does they do have interference, then wave do diffract, and wave polarize. Alright, so let's move on. Alright, so as you can see here, so if the light passes through a single slit, so there will be one part of your one part of the image will be lighted up, and the rest of the image is dim. All right, next one. Now if you do some diffraction, so if the light undergo diffraction, what you can see here, when the light passes through a single opening, then what happens here is it creates multiple light images on the background. Alright, there are some dim spots, right? So there are some dim spots, and there are some brighter spots in the image. Alright, so typical property of your wave. Alright, next one. Diffraction occurs when a wave passes through an opening not too much wider than the wavelength of the wave. So meaning to say, if an opening is smaller than the wavelength of light passing through it, so meaning to say that the light will undergo, or the wave will undergo, not only light, the wave will undergo diffraction. So it will likely to bend and create such image like this one that we have right here. Okay, so that is diffraction. And observing this diffraction, this phenomenon that we have right here, tells us that light is a wave. Right? So light is a wave. Okay. So as you can see here, when a light passes through an edge, like the one that we have right here, so when you can see some patterns, rippled patterns on your image. So meaning to say, when you see such pattern like this, it happens like the light passes through a certain edge and then they are interfered somehow, or the edge has something to do with this particular ripples, and these particular ripples are product of what they call diffraction. All right, so next. Yeah, so as I've said earlier, the edge of the shadow has ripples on it. So this one. Okay, next. Ripples are caused by diffraction. Okay, next. Now, as you can see here, when you shine a light on a round object, all right. So what would you expect? You will expect that all of are dark. All right. The shadow that will be created by that round object that we have right here, are all dark, but it is not like that. So when you shine a light on a round object, there will be a bright spot at the middle. All right, so what is this bright spot at the middle? Again, we are talking about diffractions here. Now, in this case, on the blade that we have right here, as you can see, you see some ripples of light on the edges of each of the shadow. So as you can see, if those ripples are present there on the image, so meaning to say it has the light undergoes refraction. Now when the light passes through an opening, a slit, somehow the light undergoes diffraction as well. So as you can see, from the middle, which is the brightest, and as you go further away from the middle, it becomes more dim. Alright, so this three images that you have right here is an example of diffraction. Alright, so let's go. Okay, so the GIF that you see here, this is an example of diffraction. And this double slit experiment is created by a physicist named Thomas Young. All right, so we will have it. We will have him later on this lesson. So when you fire an electron and it passes through the slits, the electrons will undergo some sort of interference and will create these patterns on the background. All right, so next. Now, the physicist who experimented this phenomenon to prove that the light is a wave is none other than Thomas Young. Alright, so he proved that the light is a wave by shining up two beams of light on a particular slit, and somehow, just like how wave behaves, they interfere with each other. So when they interfere, that's the time that you will think that only water and sound waves does that. But also, if you happen to see that one on light, the light also interferes. So meaning to say that the light is also a wave. Right, so now, at first, okay, so if you are not expecting, or if you are expecting that the light is a particle, so when you shine a light on a slit or an opening, there will be only two light that will pass through. Alright, so there will be two slit that will pass, or that will be shined on the background, or on the background. So now, if you are expecting that the light is not a wave, but if the light is a wave, you should expect that when you shine a light on a two slit opening, you can see a lot of bars at the back of, or at the image background. All right, so you can see here, it is arranged from brightest to dimmest. Alright, so if light is a wave, so based on Young's hypothesis, he thought that light should form this one. Alright, or should I say his hypothesis, he thought that light is not a wave. So he expect that the light should, if he shine a light on two slits, it will come up with this outcome. Alright, so let's see what this experiment looks like. Alright, now, after the experiment, alright, he allowed the sunlight to pass through a certain slit. And then after passing through a single slit, he let those light pass through again another slits. This time, from single slit, this we have now the double slit. All right. So what happened is, there are some unusual pattern that is observed at the background. Okay. So he tried opening the right slit. So obviously, there will be light on this particular background. Okay, now when he opened the left slit, just like the first one, it is expected that it is the same thing. But if both slits are open, yeah, if the light is a particle, then therefore the background should be like this. But what is observed is, when opening the two slits, there are parts on the background that are brighter and there are dimmer. So what does it mean? So it means that the light undergo interference. So when the light undergo interference, we can think that the light is a wave. All right. So that is what Young saw in his experiment. All right. Next, what do we have right here? We call this one, much complicated version of diffraction. We called it diffraction gratings. All right. So diffraction grating is a series of thin parallel grooves on a piece of glass or piece of plastic. All right, so these are some form of a slit that can be found on a glass or a plastic. All right, so similar to your diffraction, there will be a small opening, slit opening that correspond to a certain wavelength of light. All right, so technically this is not just one, not just two, but multiple slits. All right, there are multiple slits on a particular surface of a glass or a plastic. Okay, so here we go. Okay, so since there are multiple slits, so there will be multiple patterns that can be seen on the background. Again, just like the first one, the middle one is brighter than the sides of this middle part. Okay, so that is diffraction grating. Now, one example of diffraction grating is the, yeah. Okay, one example of diffraction grating is the one that we can see on the surface of your CD-ROM or DVD-ROM. So this light that we have right here is a product of diffraction grating. So as you can see, the light are arranged based on the wavelength passing through a certain slit. Now, what causes this particular phenomenon? You know that there are some pits. There are some pits on the surface of this CD-ROM. The pits look like this. Alright, so much smaller than this one, and it contains magnetic information about what is the CD, what does the CD-ROM contains, so like a program or other stuffs. Alright, so these pits acts like a slit, similar to this one that we have right here. They acts like a slit, and they produce enough colors of light that will correspond to certain wavelengths. As you can see here, the lights are arranged in a certain wavelength. So as you can see, we have it red, we have the orange, then we have the green on this side. Now on this side as well, we have the red, we have the orange, we have the yellow, and we have the blue. So again, they are arranged by wavelengths. Alright, so this is what they call your diffraction grating. Okay. So we go now to the next. Now, upgrading the diffraction pattern or upgrading how diffraction occurs, we can come up with a more sophisticated equipment that can somehow arrange or somehow what do you mean by I forget the word. Okay, somehow arrange properly the light according to their certain wavelength, or should I say analyze certain spectrum in a particular or in a given light. All right, so we call that device spectrometer. Alright, so from the word itself, spectrum means spectrum. So it can create some sort of a spectrum out of a single light. Alright, so, and how do you create spectrum on that? Again, by the use of this diffraction. Alright, next. Okay, so if you want to use the spectrometer, so if you want to analyze a certain color of light, for example, we have white light here. Now, as it passes through certain diffraction, certain openings that we have right here, it will likely to diffract. Now, what is on the middle is the usual white light, and what is on the side will be the certain wavelengths that the light, this particular light is made of. Okay, so that's technically how spectrometers work. Okay, so with that, we can now arrange. All right, we can now arrange the certain light patterns that we see on the background. So again, this is not by coincidence. The wavelength are also arranged in the process. So when we do diffraction, it is automatically, the wavelengths are automatically arranged, and they are separated. All right, the colors are separated from each other. All right, so that is how spectrometers work, and we can use spectrometers. All right, we can use spectrometers on some elements, and we can find out that these elements have their own unique color signature. I will give you one example, that the sodium, the color signature of the sodium is somewhere here on the yellow region. Alright, now the copper has a color signature of green somewhere here on the green region of the spectrum. So this is your copper. Alright, there are some elements that gives off blue unique color signature. The beryllium gives off red color signature. The rubidium also gives a brighter red color signature. That's the reason why this called it ruby. Yeah. Alright, so we can use spectrometer to find out the unique lines or the unique spectrum on each element. These elements or this spectrum are uniquely seen on a particular element. No element has that particular spectral lines. Okay, next. Alright, so doing so, this is the process that we have right here that I'm talking about earlier. So you put the element here, then you use a Bunsen burner. Alright, so when you use a Bunsen burner, it creates a single color of light. So when the element creates a single color light, for example, you pour this sodium on flame, it will create a yellow color. Then it passes through the slit, and those after passing through the slit, it will pass through a prism, and the prism will separate the color band of that particular light, which is in case we have here yellow. So the yellow light. Alright, so the yellow light will pass this slit, and then it will undergo dispersion on this prism that we have right here, which we called it dispersion. Okay, so we called it dispersion, and once it undergoes dispersion, now that element has a unique color pattern that we have right here. So whatever color patterns that is seen on the background, that is unique on each of every element on your periodic table. Alright, now not only element, also we can use diffraction or the spectrometer in gauging the color of your stars. Alright, so the one that you see here, the one that we use right here is the way or the process of gauging the color patterns of the star. So meaning to say that if we get the spectral lines of each stars in the galaxy, we can find out what kind of element are they made of. Okay, so there we go. So yeah, so we have here the iron. So this is the color fingerprint of your iron. No other elements have that kind of fingerprint, and lithium has this as well. Neon has this one, and our sun has this one as well. Okay, so as you can see, no fingerprints are the same. They are uniquely present on one entity, right? So that is how spectrometer works. Okay. Okay, so the black portion. All right, so the black portion spectrometer results in the sun are signatures of iron composition present in the sun. Okay, so these are the patterns that can be used to detect how many iron element are starting to grow or are starting to be found out in the sun surface. Okay, so next one. Alright, so a typical wave, so since we talked about last time that the electromagnetic wave is a transverse wave, then therefore if it is a transverse wave, alright, so if it is a transverse wave, then therefore it can be polarized. So this is one property of a transverse wave called polarization. Alright, so how do we, what do we mean by polarization? That is the orientation of the light. Okay, so polarization is a property uniquely present to transverse wave. Longitudinal wave doesn't have this kind of polarization thing that we have right here. Alright, so just like what I've said earlier. Okay, so the orientation of the light. Okay, so the orientation, there are different orientation in your light. There is a vertical and there is what they call horizontal orientation or polarization. Okay, so that's how your light is oriented. Now with the use of polarizers, that the one that you see on polarized sunglasses, now these polarizers allow certain of light to pass through a certain material. So meaning to say the light which has different orientation, they are filtered out so that the light will not be so likely to be so intense when it passes through, it's either your eye or something other materials. Alright, so when the light passes through our polarizer and exit on the other side, it is now called polarized light. Right, so here we go. Now, in an unpolarized light, there are a lot of orientations found in your light. Now, if the polarizer is used to filter out vertical orientation of your light, then therefore, what is left behind is the horizontal orientation of your light. So, meaning to say, if the next part is your eye, if this is your eye, then therefore, the one that will pass through your eyes are the horizontal orientations of the light. Okay, so meaning to say that the light is filtered. Okay, so next. So as you can see on this picture, there are the light here is intense. Alright, so the light here is intense, so that is why it is so much brighter than usual. Alright, so if we use our polarized glasses, now that intensity of light that we have earlier will be lessened. So as you can see on this third image that we have right here, the light on that image is the intensity is somehow decreased because the light is already polarized. Alright, so the light is already polarized. Okay. Now, one application of polarization is the LCD. Yan. So, LCD display. Okay. So, LCD monitors, LCD screens. Okay. So, they use the process called polarization. Okay. Next. Yeah. Another example of polarization is scattering. Alright, so scattering. Now, this will answer the question why the sky is blue. Okay, so why the sky is blue? Because if you look at the sky, the atmosphere, alright, so the atmosphere scattered effectively the blue and allowing the red light to pass through. Okay, so when the blue light are effectively scattered, then therefore what should be the color of the background? So it will be blue. Okay, so the light will just pass through the atmosphere. Okay, next one. Now that is why the sky is blue. Why is the sun red during sunset? Now the sun is red during sunset. It's because Since the okay, so since you are standing at different position, just different position, unlike the first one, so the one that we have right here. So if you are standing and the sun is in a different position, this time the blue is effectively scattered. All right, so the blue is effectively scattered, the same as the first one a while ago. And the red, since the red is not scattered, then it will pass through and then it will hit your eyes. All right, so you will now see, all right, you will now see a red sun during sunset. Okay, so meaning to say that the blue light is already the blue light are effectively scattered, leaving the red one passing through, and be able you to see the redness of the sun, which is not, the sun is not red naman. So yeah, so that's the reason why the sun looks red during sunset. Okay, next one. All right, so that is your, all right, so that is your polarization. So when, all right, so when an electromagnetic wave undergoes diffraction, undergoes interference, and it undergoes polarization, or it becomes polarized, then therefore we can say that light is a wave. Now, for us to see what diffraction looks like, so all right, we can now so we can use, all right, we can use this simulation. Yeah. So we can use this simulation here to see how diffraction works. All right. So in this case, we will use water wave. So we are the water wave. The water is just a water wave is just the available one here. We don't have the electromagnetic wave. Now suppose that the wavelength, the wavelength of the slit that we will use is somehow one half of the incoming wavelength. So meaning to say it is much smaller than the usual. So as you can see, all right, so as you can see here, that the wave starts to bend on the other side. All right, so the wave starts to bend on this side. Then what will happen? Okay, so if this is a light, so it will print. So we have one slit only, so it will print on the other side the image. So probably if this is a light, so this background from this point until and up to this point is somehow brighter. Now what if we put this one, all right, so we have a single slit and we have yeah, okay, so we have here a yeah. All right, so as you can see here, as we increase all right, so as we increase the width, all right, so as we increase the width of your slit, so the one that we have here is larger than the first one, so the diffraction pattern, so as you can see, so the diffraction pattern is much larger than the first one. Okay, so and all right, so and the intensity on both sides is also somehow larger than the first one. So as you can see, on the first one we have it until up to this point, but if we increase the slit opening or slit width that we have right here, so it will affect how many or what size of the wave will pass through that particular slit. So more so, if we use right, so I will delete this one. More so, if we use a larger one, which is much larger than the wavelength of this wave that we have right here. Okay, so as you can see, what do you expect? You can now have larger, okay, even larger wavelengths on the other side. All right, so there we go. Okay. So now let's take a look at the interference. So okay, Now, let's take a look at interference. Now, for example, we have here two slit openings. Okay. Yeah. Suppose this is the light waves passing through this, slit that we have right here. Now, as you can see, yeah, yeah. As you can see, the one that is on the middle, or all of the waves that we have right here undergo interference. We do have two types of interference. We have destructive and constructive interference. Now, if this is light, not water, the one on this side that we have right here is dimmer than the one at the middle. The one on the middle is brighter than the one on the side. Why? Because the interference, the type of interference happening at the middle is constructive interference, while on the sides are destructive interference. That's the reason why it is dim than the middle. Alright, so that's how interference work. Now let's take a look at other wavelengths. So as you can see, if you enlarge those, if you create a larger slit, it will create different patterns. Okay, so as you can see here, the pattern is different from the previous one. Okay, so there we go. So that is the wave properties of light. So what can you say? Is the light a wave? Okay, so just write it down on the comment section. Alright, so if you learned something from this video, just hit subscribe and like. So we have more videos to come, so don't forget to smile. And that's it for today. So see you later.